Welcome back, everybody. Today's lesson I like to call Rules of the Rocks, how geology has unlocked the past. First, let's start out with a little bit of history. James Hutton. Until 1800, many believed the Earth to be only 6,000 years old. This was recorded in the Bible, I believe. Scottish geologist James Hutton helped to change this idea in 1795. He roamed the countryside of Scotland on a horseback and paid very close attention to all kinds of evidence in the rock that showed that the Earth must be much older than 6,000 years. Now, along with this came some concepts, some ideas, some laws that we're going to be learning today. The first of those is an overall concept called uniformitarianism. And this is the idea that the Earth's processes that have shaped the land in the past are the same processes as today, like erosion and weathering and deposition. And they act slowly so as to appear not to occur, yet they are occurring. So if we can understand by looking at rocks today what's going on, we can learn just what's happened in the past. The present is the key to the past is another way of thinking about this. When studying the history of Earth, geologists must be able to place items or events in a particular order, a sequence, so we can determine which event happened first, next, so on, until eventually the last layer or the last event. And we can do this in two ways. The relative age, this is kind of like you are younger than your parents, but you're older than your baby brother or sister. That's relative age, it's not your exact age. Or we can look at the absolute age of these events or rock layers. And that's a much more complicated process using dating techniques we'll learn about towards the end of this unit. And in this unit, I'm going to be referring to rock strata, rock beds. Both those just mean layers of rock. Speaking of layers of rock, first law. This law is called the law or principle of original horizontality. If undisturbed, sedimentary rocks will form in horizontal layers. See them right there, horizontal layers. And that's because they're made underwater. When they settle to the bottom, they're nice and flat. You can see right there these flat layers all over the place. We've already been dealing with this throughout the course. My home on wheels there in the summertime. Here's some horizontal layers, but they don't look horizontal anymore. You notice they're tilted up at an angle, and we'll learn about tilting today. Superposition, another principle or law. This says that rock layers on the bottom are older than the rock layers above them, provided nothing's happened, they haven't been overturned. And so in this picture you can see the oldest rock layer, the shale, is on the bottom, and that sandstone is the youngest on the top. Same thing in this picture here, this photograph in Utah. The youngest layer on top there, the oldest layer on the bottom, and there's that ancient fossil there. Haha. In this picture you can see some layers of rock with dates. And notice we know the age of the granite's 85 million years old and the lava's 80 million years old. So if we wanted to know how old layer 3 was, it would be somewhere between those ages, maybe 82 or 83 million years old. The limestone, on the other hand, has to be younger than 80 million years old, like 79 or 78 or somewhere in there, because it's on top of the lava flow. So here we have some horizontal rock layers where they were building this dam. We have the oldest and the youngest on top. Watch out for overturned folds. In this picture you can see a massive overturned fold. The rocks up here look like they'd be the youngest, but actually they were below some of these rocks. So these rocks here are younger than these rocks here, even though these are above them, because this whole thing is flipped on itself. Now that can happen in this picture too. This diagram, it's an old Regents question, shows bedrock layers found in an outcrop. You got 3 index fossils are found within the bedrock layers. So these fossils should only be in one layer because they're index fossils. Yet this is also found up here, and the Eurypterid is found right here. So if we think about what's going on here, this layer is the oldest, but it's also on top, which should be the youngest, but it's not, because these things flipped. They flipped right on top of this layer right here. So this is an overturned fold, and that's the evidence for crustal movement. The index fossils give it away. Rock types help too. They're, this is shale down here and that's shale up there, but what really gives it away is the index fossils. Okay, next principle or law is the law of cross-cutting relationships. This says that faults, intrusions, and veins are younger than any layers they cut across. So this here happened after these rock layers that were put there. Okay, this fault happened after these rock layers and this intrusion because it cut the intrusion. And you can see here that this fault happened after these rocks were put there because it faulted them all. So you can't have a fault cutting through rocks unless you had the rocks there to fault. You can't fault thin air. Okay, youngest to oldest, arguably this right here, this rock layer could be the oldest, 1, then maybe 2. It could be reversed, but that's unimportant right now. There's some evidence missing that proves that. Then 3, the next layer, 4. This is also 3 over here, by the way. There's no marking for it. 5, and then we know that the intrusion must be 6 because the last step, this big fault, cut the intrusion in half. So this is 7. And that would be the order of events. Now, this might be 1 over here, this might be 2, but we're missing some evidence here to prove that. Moving on. You can do the same thing here. You got 1. Perhaps 2, because this is uplifted. 3. This fault, if we counted as a step, would be 4. And 5 and 6. Same thing here. 1, 2, 3, 4, 5. But then this contact metamorphism from this intrusion of liquid rock that came up through the other rocks cooked all these rocks over here and over here, which means it came after these, but it didn't cook this conglomerate layer right here, layer A. So therefore, the layer A came after the intrusion. So we know that 6 is going to be this intrusion. Cuts across the other layers there, but it doesn't cut across layer A. Then we got 7, 8, 9, 10, and perhaps this could be 11. Now this could have also been 8, perhaps 8, but we're not sure. There's not enough evidence to prove that. But either way, it works out. It's not breaking any laws here. Moving on. Law of inclusions. Anything included in a rock layer must be older than the rock layer itself, like these rock fragments. Those orange rock fragments there represent pieces of rock A that have broken off and been included in rock B. But because rock A is below rock B, it's older, and those inclusions must also be older. So essentially this law says anything included in rock layers must be older than the rock layer it's included in. We can see that in this photograph here. There's some boulders stuck in lava, and that particular boulder the arrow is pointing to must be younger or older than the lava itself. The lava, the rock that it's included in, is the younger rock. So the boulder was old, it broke off, and the lava has embedded it inside. Unconformities. Now, there are different kinds of these, but we're going to just kind of simplify it and call them unconformities. These are rock layers where there's a gap between one layer to the next, showing erosion, uplift and erosion. And you can see it in this picture here where it's labeled unconformity. There's a major gap there. And it's that line, that squiggly line right here, kind of goes across. And this rock layer here was folded by, tectonic processes, collision usually. And then it uplifted above the ocean and eroded where there's lots of weathering and, erosion. And then it probably went back underwater, a term we call subsidence or submergence, and new layers were deposited on top. Remember, you can only deposit those layers underwater if they're sedimentary. Different types of unconformities. There's an unconformity there if you follow the arrow. And so geologists don't like these because it's missing all kinds of history. All that rock that was uplifted and eroded is gone now, and we're missing out on what fossils and other things could be in there. Here's another type of unconformity in the Grand Canyon. Here's an unconformity between the Erie coal and the Freeport sandstone. And you can see how all those layers beneath looked like they were folded, and when they were folded, they were exposed above the water and eroded away, and that's why there's that squiggly line. Then they must have been submerged back underwater because the Freeport sandstone is made underwater, and that's on top of it all. So there's your unconformity. Same thing there, just more examples of unconformities. Always look for these wavy or squiggly lines. Here's a good question. What geologic period's missing? Well, we have the Cambrian period, which if you look in your reference tables is the first of the periods. And then we have the Silurian period, but there's something missing in between. Now, if you look in your reference tables, you can figure that out. In fact, we could pause the video here, you could check it, and when you come back, you would find the Ordovician period is missing. So it's been uplifted and eroded away. And that is it. Hopefully you guys learned some rules of the rocks.